Hello, everyone. Welcome to the April 20th edition of Math 262. Reminder, you have WebAssign due on Friday. This is our last full week of class for the semester, so you're almost there. Congratulations. We just have a little bit more to learn that I don't think you'll find to be too bad. So last time we talked about parametric equations, and today we're going to do the calculus with them. Last time was mostly graphing and algebra. Now we're going to talk about derivatives. So let's say we have a parametric curve, and we know that our x-coordinate is determined by some function f, and our y-coordinate is determined by some function g. We're going to, throughout this discussion, assume that the derivative of x with respect to t is not 0. Now, we need to work with the derivative. We know from Calc 1 that the derivative, dy dx, is the limit as delta x goes to 0 of the change in y over the change in x. So for us, the change in y is going to be the same as the change in my function g and the change in x is the change in my function f. And we're going to do a little graph to show you what this looks like. So let's say I have a parametric curve. This is time t. This is time t plus delta t. This is the point f of t, g of t. And this is the point f t plus delta t, g t plus delta t. And we see that the change in x is right here, and the change in y is right here. And you get the exact expressions I wrote above. So what does this tell us? Well, we can take our limit that we're used to, and we can rewrite it in terms of t. And what we get is we get the change in the function g divided by the change in the function f. And we're going to multiply the numerator and the denominator by 1 over delta t. And we get the limit as t goes to 0, well, delta t goes to 0, of the change in g over delta t over the change in f over delta t. Okay, and we're going to write one more thing so that you can see what's happening. We have a fraction of limits. We can take the limit of the top and we have the limit of the bottom. So now we want to know can we recognize this? What does this look like? Well, the top part is something you've seen in calculus. It's the derivative of g, and the denominator is the derivative of f. And so that's the same as dy dt over dx dt. And that is how we get the derivative, the slope, of a parametric equation. So that's our theorem. The first theorem of the day is that if x is f and y is g, then the slope of the curve at xy is this lovely expression. Okay, provided the change in x with respect to t is not 0. So we should do this with an example. So we should find the tangent line of the equation x equals cosine of t, y equals the sine of t, where t goes from 0 to 2 pi. And we're going to do it at the point 3 pi over 4. So the first thing we need is our point. That's the first thing we always need with a tangent line. We need the point. And so what we're getting is we plug 3/4 pi into x. We plug it into y. And I think you'll see that you get negative root 2 over 2, root 2 over 2. And then we need to take the derivatives. dx dt is negative sine of t. dy dt is cosine of t. So we need to find our slope, and that's the derivative of y with respect to t. So it's going to be the cosine of 3 pi over 4. And this will be the negative sine of 3 pi over 4. And I think what you'll find is this is negative root 2 over 2. And the bottom is also negative root 2 over 2. So you get a slope of 1 for your tangent line. And this tells you the equation of the tangent line. Root 2 over 2 is 1 times x minus a minus root 2 over 2. And that's the equation of our tangent line. So I'm going to give you an example to work on. And I want you to find the equation of the tangent line to the function x equals the cosine of theta, y equals 4 times the sine of theta at the point, let's see, root 2 over 2 to root 2. So this will require you to solve for t, but I don't think you're going to find it to be too difficult. Okay, so that was first derivatives. But what about second derivatives? Well, let's do an examination and see what happens. We know that the derivative of the function y is equal to the derivative of y with respect to t over dx dt. So let's let y equal h and y prime equals h prime. What's the derivative? Well, the second derivative of y is just the derivative of the first derivative of y, which is the derivative of h prime of t. So what our equation above is telling us is that we merely substitute h prime of t in for y, and we get the derivative of well, sorry, I made one minor mistake here. Let me fix this real fast. Let's put an x right here. Made one minor mistake. Here we go. Okay, So we take the derivative of h prime of x over the derivative of x with respect to t. In other words, the second derivative is obtained when we take the derivative with respect to t of the first derivative of y with respect to x over dx dt. So let's put this to work. So in summary, the second derivative of y is the derivative with respect to t of the first derivative of y divided by dx dt. So let's use this to find the concavity of our curve from earlier. When t is 3 pi over 4. Okay, so, well, first off, we need to find the derivative of y with respect to x, and that's dy dt over dx dt, which is, let's see, we've got the cosine of t over the negative sine of t, and that is, we'll just leave it at that. So now how do we find the second derivative? Well, the second derivative is something I obtained by taking the first derivative of dy dx over dx dt. We already know that dx dt is minus sine of t. So here we have sine squared of t. And the numerator we have the derivative of this cosine is the minus sine times the sine of t minus cosine of t times cosine of t. So if I simplify that a little bit, I have a minus sign. Let's see. On the top I get, let's see, minus sine squared of t minus cosine squared of t. So we can distribute this, and we can have sine squared of t plus cosine squared of t. And that's 1 over sine cubed of t. So if I plug in t equals 3 pi over 4, this tells me that the second derivative at that time is 1 over sine cubed of 3 pi over 4, which is 1 over root 2 over 2 cubed. In fact, it's positive. Which tells us that the curve is concave up at time 3 pi over 4. All right, so an example for you guys is I'm going to give you your function from before. And I want you to find concavity at the point root 2 over 2 comma negative 2 root 2. So you'll have to use the equations to find at what time that occurs. All right, so now we know how to take first and second derivatives. But there's actually something odd that can happen sometimes. Sometimes you can have two different tangent lines same point. It makes sense why this can happen for parametric curves, because a parametric curve can go through the same point twice at two different times. You can walk around and you can pass through the same spot twice, but you came through at different times. And your direction might be different at those two times. So let's do an example where we look at the curve x equals t squared minus 1, and y is t cubed minus t. So look at the values when t equals 1 and t equals minus 1. What do we notice? Well, at t equals 1, x is 0 and y is 0. When t is negative 1, x is 0 and y is 0. So what we see happening is this curve is going to go through the origin twice. And let's find the tangent lines at those 2 points in time. So dx dt is just 2t, dy dt is just equal to 3t squared minus 1. So this tells us that dy dx is equal to 3t squared minus 1 over 2t. So when t is 1, what we get is a slope of 3 minus 1 over 2, which is 1. And when t is minus 1, we get a slope of 3 minus 1 over minus 2. So a slope of negative 1. So the tangent line here is merely y equals x, and the tangent line here is y equals minus x. So let's open up Desmos and see what this looks like. You can actually graph parametric curves in Desmos pretty easily. So let me open up Desmos to show you what this will look like. All right, let's share that screen so I can show you what it looks like. So this is what the curve looks like in Desmos. And here's the curve y equals x and the curve y equals minus x. And if you zoom in, you see that what I'm going to make the black curve is our parametric equation. And the green and the blue are the two tangent lines when we go through the origin at those two different points in time. All right. So an example for you to work is the following. So I want you to find the equations of the tangent lines at the point where the curve crosses itself. So your equations will be x equals 2 sine of 2t and y equals 3 sine of t. So first you're going to need to find the point that it goes through twice, and then you're going to need to find the two equations of the tangent lines there. All right. So we're doing pretty well today. There's just two more topics we want to talk about. And the first is arc length. It's going to turn out that arc length for parametric curves is actually a lot simpler than it was for our rectangular coordinates. So recall that the formula for arc length from the very beginning of the semester was the integral of this expression right here. So we're going to replace dy dx by dy dt over dx dt. Okay. So let's see what happens. Oh yeah, we also have to replace. So if note that if x a function of t, then dx is going to equal f prime of t dt, and so dx is going to be dx dt. So anyway, all that tells you that this integral from before we can simplify. We can do a little algebra. And we see this part's inside the square root, and it will cancel out with this piece because the other piece is outside the square root. And so what we're getting is the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. And this formula looks a lot better than our formula did from before. And so our equation for the arc length of a curve C, where our t values go from a to b, is the integral from a to b of this nice expression. And that's our equation for the arc length. So let's do an example, see how it's done. Let's do it in this range. So let's find out. Well, dx dt is minus sine of t. dy dt is the cosine of t. So this tells us that the square root of dx dt squared plus dy dt squared is going to be an expression that you're going to like. Because it's the Pythagorean identity. And so we get that this square root is always 1, which tells us that our arc length is just integrating dt and so we just get an arc length of pi, which makes sense because we were looking at the arc length of half of a unit circle. So I wanted you guys to do an example where you find the arc length of this equation on the interval -1 to 3. All right, last but not least is area of a surface of revolution. And we talked about this briefly at the beginning of the class too. So we're not going to go through the derivation, but it's just as easy as it was before. So we have a curve defined by these equations on the interval from a to b. And you need to know that doesn't cross itself. So we need to find the area S of the surface obtained by rotating your curve around axis is given by this equation when you've rotated it around the x-axis. So you see it's very similar to arc length. And we get a different equation that's super similar when we rotate it around the y-axis. Okay, we'll do one more example. So we're going to go back to our favorite curve, cosine of t, sine of t, on the interval from 0 to pi. And we want to find the area of surface obtained by rotating our curve around the x-axis. Okay, so, well, we already know that the x dt is minus sine of t, the y dt is the cosine of t, and we already know that this expression comes out to be 1. So what this tells us is that our surface has area 2 pi times the integral from 0 to pi of f of t. Well, what's f? F is the cosine. Sorry, excuse me. G. G is the sine. Because we're rotating around the x-axis. All right. So the integral is the negative cosine. We evaluate from 0 to pi. This is 2 pi times minus the cosine of pi minus 2 pi minus the cosine of 0. This comes out to be 2 pi plus 2 pi, which is 4 pi, which is exactly the surface area of a sphere with radius 1. So one example for you is to find the area of the surface generated by revolving the curve around the given axis. The curve is going to be x equals 2t, y equals 3t. T goes from 0 to 3. And you're going to revolve it around the y-axis. Let me know if you have any questions, and I will see you in class.